Hello. In this video, I'm going to solve the lightning problem. So I recommend you do these problems before you watch the video, but here's the solution. Okay, so this problem it asks in one one common way to determine the distance to a lightning strike is to count the number of seconds between when you see the light and when you hear the thunder. So you see the light and you start counting 1001, 1002, and 1003, and then like you hear the thunder, you know from that time how far away it is. So we're gonna work with that. Okay, this works because when the lightning strikes, it emits both sound and light, and they travel at different speeds. Namely, the light travels faster. The light arrives at your eyes before the thunder. Okay, the first part of this question asks us to write an expression for the distance to the lightning in terms of the speed of the sound, Vs, the speed of the light, C, and the time T between when you see the light and hear the sound. And we're given several options. So A, B, C, D, E, F. So I'm going to do this solution two ways. I'm going to do it by doing limits first, considering the limits of each of these expressions first, so I can rule out which ones are which. Then I will go back and actually do the solution by working it out the same way you would if you weren't given possibilities. Okay, so first let's do it by process of elimination using limits. Okay, the first thing I'm going to do is I'm going to try the limit. Let's try the limit. Let's say the lim that C is much bigger than Vs. This is actually kind of true. Speed of light, C, is actually much faster than the speed of sound, as you can see in part B, or part 2 of this question. So in this limit, okay, so let's just ask ourselves this limit. Let's think about it. If the light was much more faster than the sound, the light would essentially get to our eyes instantaneously. Then the distance that the lightning is away from us would just basically be entirely determined by how long it takes the sound to get to our ears. The light would just get to our eyes instantly. So then we could just use distance equals VST. This is just a rearrangement of VS equals distance over T. So it's that same thing. So basically, if we're only worried about the speed of sound, then that should be the result. Okay, so which A through F agree with this statement? Okay, so A does. Okay, B does as well. You can notice if C goes to infinity, then C in both the top and bottom get large. VS is irrelevant because it's C minus VS. Who cares if it's minus VS? C is much bigger than VS in this limit. So then it would you can just throw away the VS and you get C VST over C. And then the C's would cancel. So that guy is actually okay as well. Okay. Similarly here, it's just plus instead of minus. Once again, the VS would be irrelevant. So that one also has this limit that if C is much greater than VS, then the answer is just X equals a VST. This one is not, because if for D, if C is really large, then the second term is vastly bigger than the first term, and it tells us that the distance is negative CT, which is patently wrong. So that's out. Okay, this one would tell us if C was much larger than VS, this would be 0, because C is much larger than VS. It makes the answer really small. So no. This one would get really big. Not to mention these last two have the wrong units. They both have units of time on the right and units of distance on the left. Because the V and the C have the same units, so they cancel, leaving position or distance X equal to a time T. Can't do that. They have different units. One is meters, one is seconds. Okay, so you can rule out E and F from units. You can rule out D due to this limit. But so far, we found no way to differentiate between A, B, and C. Okay, so that helps. We're taking an SAT. That would give us some help, allow us to make some of it, I guess, but we want to get the, figure out which one it actually is. Okay, so let's see, what other limit can we try? Well, let's suppose the light was just barely faster than the sound. I mean, that's not the case. We know what light and sound are, but I mean, you can imagine a universe where that's the case. In that case, the light and the sound would just barely, suppose the lightning strikes over here, I'm over here, and one hand is light, one hand is sound. They would go just barely go faster than each other, and the time between them would be really small, unless they went a very, very long ways. In other words, if light and sound were almost the same speed, and you waited and you counted a certain number of seconds between the light and the sound, it would say that the distance to the lightning strike must be enormous, because it must have had an enormous distance for the light to get ahead of the sound, because it's only barely going faster. You can think of this as like runners. If you had two runners that were almost the same speed, and you had to wait, and you want to know how far they had to run before the faster one had a lead of, say, 2 seconds, well, they'd have to run a long ways in order for, if they were almost the same speed. Okay, so that basically says that in the limb that c is approximately equal to vs, that x goes to infinity. Not that it goes to undefined, it goes to roughly infinity. It gets big. It's actually a useful concept. So let's try this here. If vs was equal to c, x for the top one, it would still just say vst. So that's not okay. It would basically say it doesn't depend on c, which is patently not the case in this limit, because well, it has to get really big. Okay, let's look at this one. So if they were about the same here, the c and vs would nearly cancel, because they're almost the same. So one minus the other would almost give you 0. You have 0 in the near 0 in the bottom, which would give you a really large numerator. So this guy could be the case. This one, however, the possibility c could not, because then the vs and the c would be added. They wouldn't cancel each other. So that one would not get really large, but b would. So we can eliminate via this limit a and c, the only remaining option being b, which is indeed the case. Okay, so that is a way to use limits to solve a problem. Of course, limits aren't the only way to solve a problem. We could be given this problem without options A through F, and then we'd have to come up with a formula. So how would we do that? So now I'm going to do an alternative solution where I actually work out what this expression is, rather than just using deductive reasoning. Okay, so problem solving. I gotta think about how I'm going to do this problem. One of the first things I want to think about is drawing a picture. So let's draw position versus time. And we'll say time equals 0 is when the lightning strike actually occurs. It happens at time equals 0, position equals 0, and then the light travels towards us, and the sound travels towards us. We'll make the sound blue, I guess. So sound. And you can see, so this is time on the x-axis, x on the, I should say time on the horizontal axis, x on the vertical axis. So position versus time. Both the light and the sound have to travel the same distance. They travel from here to here. This is the x value we want. What we are measuring in the t we measure, meaning the 1001, 1002, 1003, is the time between when we see the light, this time here, and hear the sound there. So you can think of there being 3 relevant times in this problem. Time equals 0 when they both start. time when light arrives at our eyes and time when sound reaches our ears. So we'll call this, well, basically the time we count is the time between when we see the light and hear the sound. And we want to know x. So this is a picture, and you could use slopes and geometry and all that to solve the problem. Now that you have the picture, not exactly how I'm going to do it, but it hopefully helps us think about how we're going to do the problem. For right now, the way I'm going to do this problem is I'm going to write out some equations. Distance equals rate times time. Whoa, sorry about that. We can write x is equal to the sound times, I'm going to say t sound. So I'm going to call t sound the entire time sound was traveling, t sound. We're going to call light, the t light, the amount of time that the light was traveling. And then our t, the t that we're given in the problem, the t that we count, 1001, 1002, 1003, between the light and the sound, well, is going to be the difference between the two. Okay, so x is, this is basically distance equals rate times time for the sound. We can also do distance equals rate times time for the light. So x is also equal to v light, except for v light is written as c conventionally, so let's write that as c times t light. And we also know that t light plus t just t, the thing we're given, equals t sound. Just by this plus this is that. Okay, so we have three equations. And how many unknowns do we have? Well, we know c. C is presumably given. It's the speed of light. Vs, presumably given. Speed of sound. And t, the time we count, that we measured. The things we don't know are x, ts, and tl. So we have three unknowns, three equations. Now it's just a matter of math, eliminating equations and unknowns. We want to find x, so what I'm going to do is try to eliminate the other unknowns. I'm going to try to I'm going to try to solve for x and by eliminating the ts and the tl. Okay, so let's first let's see, how should we do this? Let's eliminate ts. Okay, here. So what I'm going to do is I'm going to plug this ts in up there, and going to write this down here again. So new equation, after I plug in, I get x is equal to vs, and then ts is tl plus t. And the second equation is just the same, x equals ctl. So I have now eliminated ts, and now I'm down to two equations and two unknowns, which I'm still doing good. I just got to eliminate one more unknown. That last unknown I need to eliminate is, sorry about that, be a brief pause here. The last unknown I need to eliminate is TL. So if I solve this for this equation for TL, let's just do it this way. Of course it does that again, sorry. If I solve for TL, I'm going to divide by C. I get TL is equal to X over C. I'm going to plug that into the previous equation, and I'm going to get X is equal to VS TL, or sorry, TL is replaced by X over C plus T. Okay, so now I'm down to one equation and one unknown. I know what X is, I know what, or sorry, I want to know what X is, VS is given, C is given, and T is given. Now I just need to solve for x. So to solve for x, divide both sides by vs minus x over c. So I divide both sides by vs, then move this to the other side, and I get that. Then after some more algebra, I get x is equal to c vs t over c minus vs. It's a bit of an algebra jump, I know, but you guys are good at algebra. Go work that one out. And that is indeed the value that we agreed upon from up here. This is the same equation, and it had the right limits. Okay, so that's that. Has the right limits. It has the right units. The c and the velocities in the bottom cancel out. You get rate times time. So yes, this does have the right units. It's got the right limits. We can now that we have a formula, let's start putting in some numbers. Basically, the part 2 of this question asks us if the speed of sound in air is 343 meters per second, roughly what it is. It depends on pressure and temperature and stuff like that, but it's roughly 343 meters per second. Speed of light is 3 times 10 to the 8th meters per second. Develop a useful rule of thumb of the form: if you count to n seconds, the lightning is blah distance away. Okay, well, I'm actually going to use one of those limits because c is 3 times 10 to the 8th and VL is 3 times 10 to the 2, basically. They're enormously different. They are a million times, the speed of light is a million times-ish faster than sound. So this c is so much bigger than this VS that you can just ignore the VS. It's tiny. I mean, it's rounding air on top of the velocity of light, which means so the this VS is essentially irrelevant, which means that this c cancels with that c, and we can just use distance equals VST. It's approximately true, not exactly true, because there's a little bit of light in there, but we can ignore that for practical purposes. For practical purposes, the distance is just equal to Vs times t. Okay, so we want to know, so basically n seconds, that means it's 343 meters per second times n seconds. We can cancel the seconds, and we get this thing in here should be 343 meters times n. And then part 3 here is, does the travel time of light matter? No. Because c is much, much greater than Vs, so c Vs over c minus Vs is approximately equal to Vst, because like I said. Okay, that is how you do this problem. There are other ways of doing this problem, but this was one approach. Thank you for your time.